Welcome to another module in this massive open online course. So, we are looking at IIR filter structures and their implementation. We have seen various forms such as the direct form 1, direct form 2, direct form 1 transpose and direct form 2 transpose. Let us now look at several examples to understand this the implementation. Okay. So, we want to look at FIR filter structures, or I am sorry, IIR filter structures. And consider, and we want to do an example problem to understand this better. So, what we want to do is, let us consider this example where we have our Hz equals 1 minus half Z inverse over 1 minus 7 by 8 Z inverse plus 3 by 32 Z raised to minus 2. So, this implies, look at this, our numerator polynomial is Pz, which is 1, I am sorry, this is 1 minus half Z inverse, and dz equals 1 minus 7 by 8 3 by 32 Z raised to minus 2. So, now if you look at Pz, now what you can see is this implies basically that P naught equals 1 and P1 equals minus half, and if you look at the dz polynomial, you can see this implies that, well, d naught is 1, d1 equals minus 7 by 8 coefficient of Z inverse, and d2 equals 3 by 32. And we can now develop the several representations. Remember, we have seen 4 representations: df1, direct form 1, direct form 2, direct form 1 transpose and direct form 2 transpose, and let us now develop the structure for each of these different realizations. Okay. So, we have df1, df2. Okay. So, our df1 direct form 1 will be as follows, that will be, you have xn fed to an adder, and you will have Z inverse, and this will go to the gain of minus half and come into this adder. This will be xn minus half xn minus 1, that will be given, that will be Wn. Remember, this is the df1. The output of this goes through another adder. Finally, you have yn, and you have the branch here that goes through Z inverse, and the gain here is minus d1, that is 7 by 8. Further, you have another delay, and this goes through another gain, that is, and here you have another adder, and this will be minus. So, we have minus d1 and then we have minus d2. Okay. So, and this will be your df1 realization corresponding to the system, and this is your Wn. Okay. And now we want to develop the, so this is basically your df1, the direct form 1 realization for the given example of the transfer function. Okay. Now, let us look at the direct form 2. Direct form 2, remember, again is obtained by interchanging the branches and then merging the common delays in this case, all right, in the case of the direct, in case of the normal realization. Okay. So, we have the direct form 2 the DF2 realization, and that is given as follows. So, we have Xn remember the delays in this are along the central path. So, this will be Z inverse minus this is minus this is just P1, that is your minus half, correct, and this will go as input to the adder, and on the other side you have minus D1, that is minus 7 by 8. So, this will be added to Xn, and then you have another delay here and you have another delay here, and you have the corresponding gain minus 3 by 32. I am sorry, this will only be 7 by 8, this is minus D1, this is minus D2, and this will be fed to the adder above, alright. And this is basically, you can see you have 3 adders and 2 delays. So, this is, so this the DF1 has 3 adders and 3 delays. And this you can see the DF2 realization has 3 adders, but only 2 delays. This has 3 adders and only 2 delays. So, you can see it results in a significant saving, because delays are typically difficult to implement. So, this results in a saving of 1 delay element. Okay. And now let us look at the transpose versions. So, we have the DF1 transpose, DF1 transpose, we have again, let us say you have your Xn, that will be, you have the adder element and the adder followed by this. So, let me just make a little room here. So, you have Xn adder and then you have to pass it through the gain stage. So, this is a delay, and here you have the gain stage, and the gain in this case, remember this will be minus D1, that is 7 by 8, and that is also passed through another gain stage that will be, so here you have an addition and that will be passed through, and here you have another delay and another gain stage that corresponds to minus D2, that is minus 3 over 32, and this will be here. Okay. And therefore, what you have, and then this is your Wn, all right, and this is now passed through another gain stage, that is there is an adder here and you have yn, and you have another delay element here. This will be, just draw it a little bit more. And this will be minus half, okay. And therefore, this is your transpose, and this can also, you can also see that this also has 3 adders, plus 3 adders plus 3 delay elements. So, you can also see this also has 3 adders and 3 delay elements. And now finally, let us see the direct form 2 transpose, which is obtained by interchanging the branches in the direct form 1 transpose and then merging the adders and as well as the delay elements. So, we have the df2 transpose, which can be derived as xn adder that gives yn, okay, z inverse, and you have here another adder, and from here what you have the gain. This is minus d1 7/8, and this gain here is minus half, that is your P1, and finally you have here Z inverse, I am sorry, this has to be just slightly corrected, this has to be your, so the gain stages are given to the adder. Okay, and this has the gain 7/8 and the gain minus half, and finally what I have over here is I have another delay element Z inverse, and I have another gain that is minus 3/32, and I have over here, correct, and this is your gain. So, this is minus d1 minus d2 is minus 32 minus 3/32, and yeah, so this is minus half, Z inverse is adder is minus 3/32, and this is your df2 transpose form, and you can see this has the fewest number, this has 2 adders plus 2 delays. Okay, so this has the minimum, this has the representation that gives the minimum number of adders and delays. So, let me just briefly check this. So, I have my df1 minus half 7/8 minus 3/32, that is correct. This is 7/8 df2 minus 7/8 minus half minus 3/32, that is the df1 transpose, which is 7/8 minus 3/32 minus half, and then finally the df2 transpose, which is minus half 7/8 minus 3/32, and that also seems correct. Okay. So, we have 4 representations, the direct forms, alright, because here the coefficients are directly given in terms of the coefficients of the actual polynomials, alright. So, you have the direct form 1, direct form 2, direct form 1 transpose, direct form 2 transpose. Direct form 1 transpose has the minimum number of delay elements, direct form 2 direct form 2 has the minimum number of delay elements, direct form 2 transpose has the minimum number of adders as well as delay elements. all right. And we have seen an example, we have also demonstrated in the previous modules, we have also seen the theory to derive these structures, and now we also demonstrated the construction of these structures using a practical exam, all right. So, let us stop here and we will look at other forms, other IIR structures in the subsequent modules. Thank you very much.